All right, ladies, I'm going to give you some notes on the first part of section 1.5. You should also certainly read this section, but take notes just as if you were in class on section 1.5. This is the first part of it. This is inverse functions. All right, I'm going to start with the definition of inverse functions. F and G are inverses of each other when the following is true. F of g of x, a composite function, f of g of x has to equal x, and g of f of x also has to equal x. And there are some slide domain restrictions on this that we will come back to, or you can read in your textbook. There's a little when that involves domain. This is the most important part. The notation that we use if f and g are inverses, or we use this notation for the inverse of f, and we use this notation for the inverse of g. It's easy to confuse that with reciprocals, so sometimes you just have to pay attention to context, but when it's in this function form, then it's going to mean the inverses. Graphically, what does this mean when you look at a graph? If the point AB is on f of x, then the point BA will be on f inverse. And we'll switch back and forth between using f and g and stating that they're inverses and just using the f and the f inverse notation. But if AB is on a function, then BA is on the inverse of that function. Again, we've got some domain restrictions coming. This is going to look like symmetry. There's going to be symmetry. They are symmetric. F and F inverse are symmetric about the line y equals x. So let me give you a graphic sample of that. The line y equals x is that 45-degree line right up the middle of quadrant 1, quadrant 3. That's y equals x. And if I were to draw a function right here, tell you that it's f, and name 3 points on that function, say for example 0, 3, 1, 4, and 2. Oh well, I just put 2 points, just 2 points on it right now. 0, 3, and 1, 4. Then if I asked you to draw the inverse, it's going to be symmetric. 90 degrees right across here like that to this point right here, which will be the point 3, 0. And this point here will go right across to a symmetric point here. That will be the point 4, 1. I got enough on there to get me what the inverse would look like. That's an example of a function and its inverse. Let me give you another one. And we'll say that's f. And this one I'm going to name 3 points on. 0, 2. I'm going to name this one here will be 3, 3. And over here we'll have 6, 4. And we'll take a look at the line y equals x. Notice that the line y equals x goes right through that point 3, 3, 3. You don't have to draw this on every time. It's just a help when you're trying to get everything to look exactly right. So if I wanted to draw the inverse of this point right here at 0, 2 would come right across here and become the point 2, 0. And everything is kind of symmetric about that. You see that symmetry from here, this, and then you folded the paper to get the exact same shape. Okay, 3, 3 is going to become 3, 3 right up there, so it's across. And then 6, 4 is going to be right here. It's going to swing back out, back in again. And that point would be 6, 4. And these look a whole lot better when they're done on graph paper. All right. Important, not all functions have inverses. Not all functions have inverse functions. You do an inverse relation, but it might not be a function. Not all functions have inverse functions. So here's an example. It's a fairly simple one, a nice little parabola. This is the parabola y equals x squared, or f of x equals x squared. And if you do the inverse transformation on this, if you were to do the graphic transformation, graph a whole bunch of points and then flip them over, you would end up with something that looks like this, okay? A sideways parabola. And this is an inverse relation, but it's not a function. Because 1x, one particular value of x, results in more than one y value. So it's a relation, but it's not a function. Okay? You need to recognize that in order for a function to possess an inverse function, it has to be one-to-one. And what one-to-one means is that any specific value of x results in exactly one value of y, and any specific value of y also results in one specific value of x, okay? So you remember the horizontal line, the vertical line test for functions. Quick and easy way to take a look at a graph. Does this pass the vertical line test? Yes, this is a function. Does this pass the vertical line test? No, this is not a function. Does this pass? This is no. This is yes. These are whether they are functions or not. And the question of whether they have an inverse or not, you can look at a horizontal line test for inverses. So if I give you this graph right here, this passes the vertical line test. This is a function, but if I draw the horizontal line test, it fails. So it is a function, but it cannot do, its inverse is not a function. Okay, a little better. Its inverse is not a function. All right, so it passes the vertical line test. It is a function, the one in black. But if I were to try to draw its inverse would not be a function. So you take a look at this one right here. It's like a nice little cubic function. It passes the vertical line test, and it also passes the horizontal line test. Any place you pass that horizontal line, it touches it exactly one place. So it's inverse. It has an inverse, and it is a function. So being able to look graphically and determine quickly, is this going to have an inverse or not? Okay, so what we do when we have a function that fails the horizontal line test, sometimes we will restrict the domain of whatever this given function is, of f, so that its inverse will be a function. So here's an example. First, the simplest one is to look at that quadratic, that parabola, f of x equals x squared. So this is what the graph looks like. It is a function, but its inverse is not a function. So we arbitrarily choose a section of the graph that would pass the horizontal line test. So usually choose something that's in the vicinity of the origin, although not always, or some important place on the graph, a maximum or a point of inflection. This is the time we're going to select this section right here. This is just an arbitrary selection. We could have also picked the other half of it. Would have done the same thing. We pick a selection and we restrict the domain. We say we are only going to look at x's that are greater than or equal to 0. Okay? We could pick the other side. That would be equally as valid. No real difference. Just pick one and stick with it. the place that you have seen this before is with the trig functions. So the sine of x is that function that oscillates, you know, and it's back over here, and it keeps going forever and ever in both directions. So obviously, it is a function, but it's not. If we flipped it over, it would not have an inverse. I'm sorry, it would have an inverse, but its inverse would not be a function. We need to pick a section of this graph that is not going to fail the horizontal line test. And the one that is generally picked for sine is this section right here. That's the one that's usually picked, although there's lots of other ones that would work. So we're going to restrict the domain here to the domain of negative pi over 2 to pi over 2. That's the generally accepted one that people use. And you did this also for cosine and for tangent. And I'm not sure if you did it for the other three, but you should have done it for the other ones besides this. Okay? Generally, good to know this, the domain of F inverse, the domain of F inverse will be the range of F. And this comes from, think about the point switching thing. If AB is on F, then BA is on F inverse. So all of the x's and y's switch places. Again, we have some domain restrictions that we have to deal with for this. Likewise, the range of F inverse will be the range of F. Okay? All right. One of the things you'll have to be able to do is to find the inverse of a function and state its domain and range. Okay? Example. Here's our given function. F of x equals the square root of 2x minus 3. So number one, note the domain of this function. 2x minus 3 has to be greater than or equal to 0. 2x has to be greater than or equal to 3. X has to be greater than or equal to 3 halves. You should also note that the range of this function is these are square root functions, so you remember what they look like. They look like this, right? So nothing's been done to the outside of it. It's going to have this basic look, and the endpoint's just going to have moved. Our y values are going to be greater than or equal to 0. You know that from your parent graphs and just basic function shifting. All right? So to figure out what F inverse is, we're going to switch the x and the y. So where it says f of x, I'm going to put x. Where it says x, I'm going to put y. Just like every point switches, we're going to say every x and every y switches. And then after you do that, you solve for y. Square both sides. And 3. Divide by 2. You can either leave it this way or you can change it to this. Either one of these is fine. It doesn't make any difference. Sometimes one's easier than the other. But really, there's no set rule for that. And then from here, you're going to state the domain. This is our new function. This is our F inverse function. I'm just going to use the first one. Okay? Now, this actual function, if it weren't an inverse, that's just a parabola. It has no domain restriction. But because it's coming from another function, because it's the inverse of another function, we're going to take its domain, x, to be the same as the range of the original function. And the range of the original function was greater than or equal to 0. So the domain of the inverse function is going to be greater than or equal to 0. The range of this function will be the same thing as the domain of the other one. So the domain of the other function was greater than or equal to 3 halves. So the range of this function is greater than or equal to 3 halves. Another example. okay? You should be able to think of, this is the given function, 2 divided by the quantity x plus 1. You should know what the domain is that x plus 1 cannot equal 0, which means x cannot equal -1. You can write that in interval notation if you want. And you should remember that you talked about the range of it as well. These kind of functions tend to have vertical and horizontal asymptotes, so this is where the horizontal asymptote is. For now, if you can't remember how to get the horizontal asymptote, go ahead and draw the graph on your calculator to help you figure out where that horizontal asymptote is. And this one, if you take a look at it, you'll see that y never equals 0. I'm just going to draw a little sketch on here of what you would see if you drew this on your calculator. It would look kind of like this, and you should recognize that there is a vertical asymptote here and a horizontal asymptote here. If you've forgotten that, how to get that without the calculator, we're going to come back to that a little bit later on. Okay? All right, so now I want to actually crunch through and find the inverse function. So instead of f of x, I'm going to change that to x, and instead of x plus 1, I'm going to make it y plus 1, and we are going to solve it for y. So we're going to multiply both sides times y plus 1. I'm going to divide both sides by x, and I'm going to subtract 1. You can leave the function like this. There's nothing wrong with that. A lot of times we're going to be working with common denominators, so this is also a very likely way of leaving the final answer. And then writing that with the inverse function notation. Okay, so the domain of this comes from the range of the original function. The range of the original function was y cannot equal 0. The domain is x cannot equal 0, which actually shows up right there. That's not always, doesn't always show up. Sometimes it's a restricted issue, but this time it showed up. And the range comes from the domain of the original function. The domain of the original function was that x cannot equal -1, and so the range of this is y cannot equal -1. And if you draw this on your calculator with y equal this, you're going to see that there is a horizontal asymptote at -1 and a vertical asymptote at 0. All right, let's consider this. F of x equals x cubed minus 1. And I'm going to ask you to find f inverse of 7. I'm not asking you to find f of 7. I'm asking you to find f inverse of 7. So this means that the point 7 comma something is on f inverse. Okay? Therefore, now know that symbol for therefore, the point something comma 7 has to be on the original function, on f of x. So I'm going to take this piece of information, go back over here, and find the point on f of x where y is equal to 7, where the y coordinate is 7. And it's where x equals 2. That means over here, this point is 2, 7. So when we go back over here, the point is 7, 2. So f of 2 is 7, becomes f inverse of 7 is 2. And that's all the notes for right now. Make sure you've read over those and are ready to ask me any questions about those in class tomorrow.